All right, so really nice work on the exam. So saw lots of good understanding, and we went through this question by question on Friday. So I just want to hit a few highlights. The power set of a set, right, is the collection of all subsets of the set. It's always going to include the empty set, and it's always going to include the set itself. And then if there's other subsets, those will be in there as well. So on question 1, we had A union B, sorry, A intersect B, and it was just a set of two things, 5 and 7. Just imagine it's up there. So things in common between A and B. Yeah. Here we go. Things in common between A and B are just 5 and 7. So all the subsets of this set consisting of two things are the singleton set 5, the singleton set 7, the original set itself 5, 7, and then the empty set, which could just be bracket, bracket, or a phi. The nested summation, right? Remember, the idea is to take the inner part and evaluate that, and then evaluate that as I goes from 0 to 3. And it's not just a sum of simple products. I don't remember what some people did, but some people just sort of wrote out 4 product terms. I think they did 0, 1, 2, and 3 together or something like that. So you got to actually nest them, do the inside and do the outside. And if you remember how to do matrix multiplication, that's basically how matrix multiplication works. The only thing that struck me on this question, so most people identified these correctly, but I also asked you to indicate whether these statements were correct or incorrect. And I saw lots of things where people said this is detachment, it's incorrect. Or this is a fallacy of denying the hypothesis, the statement is correct, right? So fallacies are incorrect, they're not truthful, right? Detachment and indirect reasoning are valid forms of logic, so those statements are correct. So, there should always be that pairing, detachment, indirect reasoning, correct, fallacies, incorrect. Yeah, 4 was fine. Question 7 I threw out. So 7 I wrote a while ago, and my intent was you would just see that 6 was congruent to 1, and this becomes trivial, right? But between the time that I first wrote this and the time that I put it on the exam, it read like this up to here, and I looked at it and I'm like, well, that's kind of subtle, I should give him a hint. And at that point I was thinking you could do this in cases, so I threw in a misleading hint here, which I did not know was misleading at the time, which was to break it into 5 cases. You cannot do this with cases though, okay? It just does not work, and here's what so if n is congruent to m, is a to the n congruent to a to the m? And the answer is no, right? This in general is not true. Were this true, then we could say, if we want to find 6 to the n, right? Well, we can break n into 5 cases, modulo 5, 0, 1, 2, 3, or 4. And we could say, 6 to the 51st is going to be congruent to 6 to the 1st, mod 5. But that's not how modulos work, right? We can do this business when we're doing addition, subtraction, and multiplication. Okay, so if n is congruent to m, then a plus n is congruent to a plus m. Right, that's absolutely true, and a times n is congruent to a times m. Right, and we can replace these specific values with anything congruent to them. It doesn't work with powers, and I'll show you a real simple counterexample. Let's just work mod 3. Well, we know 2 is congruent to 5, right? So logic would say 2 squared should be congruent to 2 to the 5th. But that's not true. This is 4, which is congruent to 1. This is 32, which is congruent to 2. Right? But since I threw in what was supposed to be a helpful hint that actually turned out to be absolutely bogus, I just threw out that question. So you got 15 points for question 7. That was my bad. I will give you a substitute question on the final, I promise. So the truth table setup, most people got this right, but I would suggest when you're doing this, don't skip steps, okay? Before you show a truth table column for this expression, show truth table columns for P and Q, and show truth table columns for not P and not Q. And before you show that, show a truth table column for not P and show a truth table column for not Q, and then AND them. Do everything in single steps, right? Same thing with implication. We know a truth table for P implies Q. We know a truth table for Q implies P. And if you take the conjunction of those, that gives you the pi conditional. But I didn't take off if you skipped a few steps, as long as you seem to be doing everything on the way. All right, so let's talk about the proof question with even odd numbers. So 2 main issues I saw. 1, writing things that were not propositions. Okay, so I saw proofs that started off looking like a proof, and then on the next line might say something like, this. Right? And that's not a proposition. It's not a declarative statement with a truth value. It's just an arithmetic expression. So if you say something like this, that is a proposition. Right? We're saying that this left side is equal to the right side. That's a declaration that has a truth value. So that's valid. But if it doesn't have a truth value, it's not a proposition. All right, the other thing, and this is the, in some ways, bigger concern, was I saw arguments like this. So we're trying to prove that if the product is even, then at least one of those numbers is even, right? So prove if AB is even, then A or B is even. So here's what doesn't work. So let A be an even number, let B be an odd number. So A equals 2 times K, B equals 2 times J plus 1. AB equals 2K times 2J plus 1 equals 2 times 2JK plus K. Therefore, AB is even, QED. Well, that's a good proof of something, but it's not a proof of what we're trying to prove. We're trying to show if AB is even, then A is even or B is even. This shows that if A is even or B is even, well, it shows that if A is even, then A times B is even. It's a valid proof of that fact, but that does not prove this. Right? So let's put this in propositional logic. B can be the proposition AB is even. Q is the proposition A is even or B is even. And we want to prove that P implies Q. What you've kind of proven in some way here, and the ors make it a little weird, but approximately speaking, what you've proven here is that if A is even or B is even, then A times B is even, right? It's the converse. And this does not prove this. And here's where this can get you into trouble. So let me show you a different question, and let's do the same kind of converse thing. Prove let me see how I do this. If the sum of two integers is even, then each integer must be even. Well, if you start off with here, let a and b be even. A equals 2k, b equals 2j, a plus b equals 2k plus 2j equals 2 times k plus j. Therefore, a plus b is even. Okay, this is absolutely valid. If a and b are even, you've proven a plus b is even. But this does not prove that if a plus b is even, a and b have to be even. Because 7 plus 5 is even though 7 and 5 are both odd. Right, so right, we've proven that if Q, then P, and that's absolutely true, but this is false because the sum can be even though each integer is odd. So converse is not logically equivalent to the original proposition in general. In particular cases it could be, but it's not logically equivalent. So those were the two main issues with the proof. One other comment, this is just kind of a detail, is this statement QED. QED is fun to write at the bottom of proofs, right? But what does QED mean? It does not mean the proof is done. Okay, it does not mean that's the end, right?
Is it similar to therefore?
No, it's more than that. QED is Latin for which is what we were trying to demonstrate. Okay, so prove blah. Stuff, blah, QED. Okay? And it's a reminder that this last statement of the proof, which says blah, that's what we were trying to demonstrate. Okay? So if you're using a proof by contradiction on something like this, you assume the negation of the condition, you go through this kind of stuff, you get that AB is odd. QED, no. You weren't asked to show that AB was odd. AB is odd, contradiction, QED. No, you weren't asked to show that there was a contradiction somewhere in your proof. You're asked to show A or B is even, right? So therefore AB is odd, that's a contradiction, therefore A or B is even, QED, right? Prove that either A or B must be even. So usually when you say QED, make sure the thing right before it is a restatement of the thing you were trying to prove. And that just kind of like nails the proof down rock solid. So that's just kind of a stylistic thing. All right, so if you have questions on the midterm, you can ask them now, or you can ask me offline. Either way. Yes?
So does the majority of the students not understand other questions on them?
I didn't look at it in great detail because so most people either used a table approach, right, which is what I was leading you to mistakenly, or did the reduction of a 6 to a 1, right, and said it was just 1 to the n minus 1. But it's conceivable that somebody might have looked at that and felt like they needed to break it into cases because that was a hint, but understood that you can't do exponents in cases like that, and that might have taken them astray. Because at first I was just going to say, okay, if they broke it into cases, I'll give credit, but it might have actually like deterred some people from being able to do that. So I just decided to throw it out. It was just my bad. So freebie. All right, so did you have a chance to watch any of the induction videos?
Watch them all.
Yay. So what are the takeaways from those? And we're going to go through all of that stuff. There's a lot of examples in there. I put those up partially because I was getting requests from people online to go over different kinds of induction. So, but we're going to go through all of that. But what were the basic takeaways, if any? Recursion. Okay, that's a big word.
They can reduce mathy problems.
Yeah, so they can reduce mathy type problems. Good.
Failure to state a proposition and proving the wrong thing are common errors.
Yeah, so common errors are going to be what we just talked about with question 6, which is either trying to prove something that goes in the wrong direction, like a converse or maybe an inverse, or as you're doing an inductive proof, failing to write propositions. And it's really tempting to not write propositions in inductive proofs, especially the mathy type questions, because we're just taking equations and combining them and simplifying them and so on, and it's easy to just start writing those down, and that can lead you astray with inductive proofs. So we'll see examples of all of those. So I don't know if I don't think I talked about this in the video, but here's a classic example of induction. You want to walk 1,000 miles, okay? And how do you walk 1,000 miles? Well, you just keep putting one foot in front of the other, right? So how do we prove that it's possible to walk 1,000 miles without having to actually take all those steps ourselves? How would you convince someone that they could actually do this? And there's really only 2 things you need, right? You need to be able to take a first step, and then, assuming you just took a step, you need to be able to take one more step. And if you know that anytime you take a step, you can always take one more step, you can prove that it's possible to take 1,000,000 steps, 1,000,000,000 steps, 1,000,000,000,000 steps. Right? And the proof is straightforward. How do you know that you can take 2 steps? Well, you know you can take your first step, okay, so that's 1. And we also know that if you can take a step, you can take one more. So you take your first step, that's 1. You can take one more, that's 2. Well, now we've just proven that you can take 2 steps. So do whatever you have to do to take those 2 steps, and now use that inductive step again. Say, okay, well, we just said that if you've just taken a step, you can always take one more. So after you take those 2, take one more, now you've got 3 steps. And you just kind of build up like this, and if you do this 1,000,000 times, you can prove that you can take 1,000,000 steps. Okay, that's induction in a nutshell. But it lets us generalize this thing that we intuitively understand, which is we can keep going, ... however you picture it. It lets us formalize that into something that is mathematically precise. So let's play with some examples of induction. And we'll do some mathy ones and some non-mathy ones, but let's start with a mathy one. Let's prove that if we add the first n integers, we get n times n plus 1 divided by 2. So for example, if n equals 3, 1 plus 2 plus 3 is 6. It's also equal to 3 times 4 is 12 divided by 2 is 6. So there's a story / urban myth, I don't know which. Well, not an urban myth, European myth. I think it was Pascal, some famous mathematician. In grade school, a teacher wanted to keep them busy, and so had the students add up the numbers from 1 to 100. And he raised his hand a minute later and had the answer. And he basically used something like this. He actually added them up in pairs, 1 plus 100, 2 plus 99, and so on. But that's another version of this. All right, so we want to prove this statement, okay? So inductive proofs are basically about stating a family of propositions and showing that every proposition in this family is true. Okay? And this is one particular statement up here, that sum on the left equals the expression on the right. But it's really a family of statements because there's this variable n, right? And let me put over here, n is an integer, and n is bigger than or equal to 1. So there's an infinite number of propositions up here. There's the proposition that 1 is equal to 1 times 2 divided by 2. There's the proposition that 1 plus 2 is equal to 2 times 2 plus 1 divided by 2, and so on. And we're trying to show that every one of these statements is true. So usually the first thing to do is to try to write a family of propositions. And so since it's a family, it's going to have a variable. So let's call this like proposition n, where n is an integer bigger than or equal to 1. And let's say let P of n be the proposition one plus 2 plus up to n equals n times n plus 1 over 2. And let's prove P of n for all n bigger than or equal to 1. And I'm not going to keep writing n as an integer, we're just going to keep that in mind. So our goal of the proof is to prove P of n is true for all n bigger than or equal to 1. Okay, so inductive proof, there's two things we have to do. So in general, to prove any P of n, and let's just say n bigger than or equal to 1, you must prove P of 1. This is a base case. Okay, this is showing that the proposition is true for one particular value of n. And that's usually pretty easy to do because it's just one statement, right? And we can certainly take this proposition here and say, is it true for n equals 1? Well, that's just the statement that 1 equals 1 times 2 divided by 2. Yeah, that's true. So the base case is usually pretty straightforward to prove. The second thing is to prove that if P of n is true, then P of n plus 1 is true. Yeah?
Does the base case have to be 1? Or
No.
Okay.
It could be anything. So I'm picking on n bigger than or equal to 1. But it could be anything. It could be 1,000. It could be negative something.
It's just easy.
Yeah. So you prove a base case, and then you prove that if this proposition is true for n, it's also true for n plus 1. And that's easier than proving that P of n is true for every value of n. This is letting us assume something. It's letting us assume that P is true for n. And the only thing we have to show is that it's true for n plus 1. So again, we're just trying to prove one particular proposition, and we're doing it with an assumption that another proposition is true. So this is usually a whole lot easier than this. But if both of these things are true, then we can wave a magic wand and say, therefore, by mathematical induction, and then we can write this, P of n for all n. Okay, so let's try this with this particular proposition. So P of 1 says 1 equals 1 times 1 plus 1 over 2. And we know this right-hand side is 1 times 2 over 2, which is 1. So proposition 1, P of 1, says basically 1 equals 1. And we're going to assume that's true, because we know that 1 is equal to 1. Okay, how do we prove if P then Q? We assume P and we try to show Q, right? So prove that P of n implies P of n plus 1. Okay, so here's our formal proof. Statement 1, P of n is true. That's the hypothesis. We want to work logically and eventually be able to write P of n plus 1 is true. As soon as we do that, we're done. Right? We've proven this. We've got our base case. We've got P of n for all n. Okay, well, what can we possibly do with P of n? Really, the only thing we can do at this point is write out what P of n says. Because if we just have P parentheses n, there's not a whole lot we can do with that. So let's write out what P of n says, which is 1 plus 2 plus n equals n times n plus 1 over 2. This is the definition of P of n. And it's really important to be clear that we have not proven this is true in all cases. Right? We've proven that this is true if P of n is true, because this is really just what P of n says. Right? But when we finish this proof, we're not going to have proven that this is actually true. We're proving if P of n is true, then all these things that follow are true. Okay, it's very subtle, but really, really huge. Okay, so we know this is true. Well, now we go to our kind of ignore area. And we're trying to prove P of n plus 1. So let's write that out. So want to show we want to show that if we add up all the integers up to and including n plus 1, we get n plus 1 times n plus 2 over 2. If we could show that from what we've already got, we'd be done, because that's P of n plus 1. So we've got something that kind of looks like what we're trying to get to. The left side certainly looks a lot like this. Here we've got the sum from 1 to n. Here we've got the sum from 1 to n plus an extra n plus 1. Right? So now you start thinking, well, how can I take this equality, which I know is true, and try to turn it into this equality, which I'm trying to show? And this is where the kind of intuition comes in. This is the part that requires some sort of trial and error, insight, intuitive leap, something. But for me, not being very creative about this, I see this, and I see this, and I say, you know, if I were to just add n plus 1 over here, this would look exactly like that. Right? And I'm a fan of progress. Anything that like moves me further along, I'll go for it. So let's just add n plus 1 to both sides. And this is the step where most proofs fall apart, because it's very tempting to write something like this, which we haven't proven yet. But we can absolutely write this if we've claimed that this is true, because all we've done is add this one value to both the left and the right sides. So does everyone see that this follows from step 2? Not necessarily why we want to do this, because it's not clear yet. But I mean, you could have added 17 to both sides, and that would still be valid. I could multiply both sides by 512, and that would still be a valid statement. But instead, I'm just adding n plus 1. And I'm doing it to make this left side look like the thing I'm after. Well, the right side does not look like the thing I'm after, but I know algebra. And so let's do some work on that right side. And let's just do some simplification on this. So I'm going to multiply this expression by 2. And divide by 2. And I'm going to combine the top. And use the common denominator. And this is all one big long equal expression, so I'm not going to keep rewriting the left side. So I'm going to multiply this out, n squared plus n plus 2n plus 1 divided by 2. And I'm going to combine. And then I'm going to factor, because whenever I see quadratics I get excited and I want to factor them. Right, so this is n squared plus 2n plus n is 3n plus, where'd my 2 go?
It should be 2 on.
Yeah, 2n plus 1, 2n plus 2. There we go. And that factors into this.
Yeah.
And hey, guess what?
We solved the event and used the event.
We wrote something over here that looks exactly like this thing. Well, the n plus 2 and n plus 1 are on the opposite sides, but I can switch those around. And I have just proven that this thing is equal to this thing. Yes?
I'm a little confused on the ignore part. Why is it n plus 1 times n plus 2 over 2?
Because P of n is the proposition that if we add up to n, we get n times n plus 1.
Right.
So P of q would be the proposition if we add up to q, we get q times q plus 1. So P of n plus 1 says if we add up to n plus 1, we get n plus 1 times n plus 1 plus 1 divided by 2.
Okay.
And we can spell that out in step 5. So step 4, we've shown that the sum up to n plus 1 is equal to n plus 1 times n plus 2 over 2. Let me put that in a different form. Like that. Right, so in step 5 I can say P of n plus 1 is true. Why? Because if you look at the definition of P of n plus 1 and you look at what we showed in step 4 proves P of n plus 1 is true. Okay, so now I can say therefore P of n implies P of n plus 1. Because we started with P of n plus 1 and we just proved P of n plus 1. Sorry, we started with P of n and we just proved P of n plus 1. Therefore, P of n for all n bigger than or equal to 1. And the reason for that is mathematical induction. And if our original problem was to prove P of n for all n bigger than or equal to 1, right, that was our very first original thing we were trying to prove. Now I can say QED. So there's this kind of mysterious step that happened somewhere right around here, where for whatever reason we decided to add something to both sides. And that sort of got us what we were after. All right, so you want to try a different one? Let's prove that if we add up odd integers up through 2n minus 1, we get n squared. So for example, if n equals 3, we're adding the numbers 1, 3, and 5, which is 9, and that's equal to 3 squared. If n is 4, we're adding the numbers 1, 3, 5, and 7, which adds up to 16, and that's equal to 4 squared. All right, so someone in the back row, give me a proposition to work with. I'll start you. Yes?
The sum of odd integers up to 2n minus 1 equals n squared.
Okay, what should we call this proposition?
P of n.
P of n, okay, so it's a family of propositions. Let P of n be the proposition. Does this make sense? Let P of n be the proposition, blah, 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 for all n bigger than or equal to 1. It really doesn't quite make sense. Because if I plug in an n equals 3, that would say let P of 3 be the proposition that 1 plus 3 plus 5 equals 3 squared for all 3 bigger than or equal to 1. And that's just kind of a little weird, right? So this is really just a statement about something if we set n equal to a particular value, right? So when we try to prove that this proposition is true for all n, we might say something like prove P of n for all n bigger than or equal to 1. But P of n itself is just one proposition about one particular value of n, right? Whether that's an actual number or it's just a symbol n, it's saying that this is a true statement. So don't put your for all n or exists in n or something like that, right? But you can do that when you're saying, let's prove P of n for all n bigger than 1 or bigger than 3 or whatever. All right, so second row, what do we start with? What's the first line of our proof?
There's P of 1.
Good. All right, third row, what does P of 1 say? One equals 1 squared. Fourth row, is that true? You got the hardest question of all.
It's true.
Yeah. Why? Because 1 squared is equal to 1, so 1's equal to 1. All right, so we know P of 1. That's our base case. All right, what's the other thing we have to show in order to complete this proof?
P of 1 implies P of n plus 1.
Yeah. And we have to prove this for any value of n bigger than or equal to 1. Right, if we can only prove it for a few values of n, we can't throw it into our inductive step. Right, we've got to show that for any value of n bigger than or equal to our base case, P of n implies P of n plus 1. Okay, so let's prove this. So what's the first step of this proof?
Add 2n plus 1 to both sides.
State P of n.
State P of n, right? We gotta start with a proposition. So P of n, that's the hypothesis. And then second step,
P of n.
find P of n. All right, and we're after P of n plus 1, which is the sum of odd integers up through 2 times n plus 1 minus 1. Right, so 2 times n plus 1 minus 1, which is 2n plus 2 minus 1, which is 2n plus 1. Right, so if P of n goes up to 2n minus 1, the next odd number is 2n plus 1. And we want that to be equal to n plus 1 squared. Okay, so now, Connor, what do we want to add both sides?
2n plus 1.
2n plus 1, right? Why?
Number.
Because we've got this part matching that part. Let's throw in a 2n plus 1 and see if we can make things happen. Right, reason for this is just algebra. We just added 2n plus 1 to each side. So this thing is equal to that thing.
Can you simplify that and just say 2n instead of having 2n minus 1 and 2n plus 1?
Not with the original proposition, because we're trying to add odd integers and 2n is going to be even. But we could pull out all those minus ones and put them together at the end to get something interesting. All right, so what can we do with this expression?
You can simplify the right side.
All right, we can just factor that as n squared plus 1, or n plus 1 squared. That's more algebra. So now we've shown that all of this stuff is equal to this stuff. So now what do we say?
P of n implies that P of n plus 1.
So I would go ahead and I would say P of n plus 1 is true. Right, that's the definition of P. And then I would say, therefore, by assuming the hypothesis of P of n, we proved the conclusion P of n plus 1. And now, having proven P of 1 and having proven this inductive step, we can use mathematical induction and say, therefore, P of n for all n bigger than or equal to 1, and that's mathematical induction. And that's what we were asked to demonstrate. So these proofs involving equations and numbers and sums and things like that all kind of look and feel like this, right? And there's just some point in here where we take a leap of faith and we say, well, I don't know, let's just add something to both sides, or let's multiply both sides by something. And you hope that it gets you somewhere, and more often than not, it actually does. so let's try a different kind of question. So here's a 2x2 tile, and we have this sort of L-shaped piece of material that looks like that. It covers exactly 3 of those 4 tiles. So suppose we have a floor and it's got 2 to the n squares in each direction. So it's a 64 by 64 or a 1024 by 1024 floor or something like that. And we have an infinite supply of these L-shaped tiles. And when we talk about tiling a floor, what we mean is taking these tiles, putting them in whatever orientation we want, and placing them over squares so that none of them overlap, none of them go outside the boundary, none of them have to get cut, and they all, you know, sit on even lines. They're not like halfway covering a square or something like that. So the usual tiling you would like to do. And the claim is that if this is a 2 to the n by 2 to the n region for any integer n, we can always cover this floor except for 1 square. We'll always have exactly 1 square left over. But if you have one particular square anywhere, say this one that you say, I don't need to cover that because I'm going to put, you know, a skinny bookshelf there or something, the claim is we can tile the rest of the floor using these L-shaped tiles. And we want to try to prove this. So other than the 2 to the n's on the dimensions, there's really no math anywhere in sight here. Right, we just got these little tiles and we're trying to put them down on the floor and cover up the region. So let me phrase this as a proposition, and then let's talk about how to prove it. So let P of n be the proposition. Given a 2 to the n by 2 to the n floor with any 1 square removed, you can tile the rest of the floor with these L-shaped pieces. So Pn is the proposition that if your floor is 2 to the n by 2 to the n, and we pick any 1 square and say, I don't care about covering this with a tile, we can tile the rest of the floor perfectly with these L-shaped pieces. So what's a possible base case here? 2 by 2. So hey, here's a 2 by 2 region. Well, if the 1 square you don't care about happens to be up here in the upper right, this is a demonstration, a proof that we can tile the rest of the floor using an L-shaped tiles, because we can just drop a tile down here. But suppose we had a 2 by 2 region where this was the region we didn't care about. Can we tile the remaining region with an L-shaped piece? Okay. And what if that's the piece we don't care about? And if that's the piece we don't care about? And are there any other possibilities? So by getting some tiles and some floors, or drawing pictures and putting some words on, right, we've proven that if n equals 1, the proposition is true. So P of 1 is true. And we can show that by looking at 4 cases. So to do an inductive proof, we need to prove P of n implies P of n plus 1, where n is any integer bigger than or equal to 1. So we're going to assume P of n is true, and we're going to try to prove P of n plus 1. Any ideas what form we could put this in to try to do something like this?
Well, we could do 2 to the n times 2 to the n equals 2 to the n plus 1. Well, not equals, but
It does equal, actually.
2 to the n plus 1.
Actually, 2 to the n times 2 is equal to 2 to the n plus 1.
Yeah.
Well, that's going to help us, actually. You got an idea?
Could we write down the two different cases in which we try to prove n plus 1 on given a certain true or false statement?
Yeah, we can break it into cases. We gotta figure out the right cases, though, right? Because I mean, we did for n equals 1 with 4 cases, but if n equals 2, there's more places that we could have a missing tile. But that's effectively what's going to come out in the end, what's going to get us to the end. So if we take that and we try to combine it with this, and this is not something that is obvious, right? Trial and error, creative leap, something. But let's do the following. Our goal is to prove P of n plus 1. So we want to show something about a tile that's 2 to the n plus 1 by 2 to the n plus 1. A room that's that big, right? So let's split this into halves in both dimensions. And now this is 2 to the n. And this is 2 to the n. This is 4 2 to the n by 2 to the n subrooms. All right. Now we got to remove one tile and then try to tile the remaining floors. So let's just suppose we pick some tile right here and we say, I'm not going to cover that one. Okay. Well, here we have a 2 to the n by 2 to the n room with one tile removed, and we're assuming P of n is true. So what does that let us conclude?
The rest of it's tiled.
It lets us conclude that the rest of this can be tiled because of P of n.
And then you put all the others in the
Yeah.
corners
And
for all
then
the
put them
different.
further.
Yeah, so now that worked great here because we were missing a tile. We're not missing any tiles from here, but let's just pretend that we don't care about this corner. Well, now this is a 2 to the n by 2 to the n with one missing tile, which means this can be tiled. Except for this little corner. And let's do the same thing over here. And so this can be tiled except for that corner, and do the same thing here. And this can be tiled except for the corner. And hey, guess what? We can tile those 3 missing pieces with a single L-shaped piece. And now we've tiled the entire 2 to the n plus 1 by 2 to the n plus 1. So we assumed P of n, and then we did stuff. And then we concluded P of n plus 1. Therefore, P of n implies P of n plus 1. Therefore, P of n for all n bigger than or equal to 1 by mathematical induction, which is what we were trying to demonstrate.
Now we know if they Tetris like
Say what?
Now we know if they Tetris like pros.
Yeah, totally. So does that seem a little weird to anybody? Yeah, good. But that's an example of mathematical induction. Yeah.
It almost seems like that's, if you were to do that, you might say, you've proven that that works for if the squares are aligned like that, and only for that. Like, what if the squares were in any other one?
Well, so okay. So first of all, we started off by assuming this was the one and only missing tile, right? And we temporarily removed these so that we could tile the remaining areas. But then we covered these with an L-shaped tile, right? So the only thing that's not covered was whatever the tile was in this upper left corner. But technically, we need to do this 3 more times. We need to say, well, but the missing tile might have been over here, right? And it's the exact same process, except we, leave these 3 corners open and then tile that and do the same thing for that. So we really need to do 3 more cases. But there was no specific assumption on where this missing tile was. And it could have been over here in this corner too, and that wouldn't cause us any problems in what we did. So as long as there's 1 tile missing from here, we can tile the rest. And you do that 4 times. Does that make sense? So it's not so much to do with math in particular, even though it's called mathematical induction. It may not have anything really to do with math per se. It's this process of proving a base case and then proving that if you know your proposition here is true, you can prove the next proposition is true. Well, let's see. So let's find a good problem to work on. All right, let's break into groups and hit the boards and try to prove this using mathematical induction.
N squared?
And plus times that 1 times.
Let's see.
I have it right here.
get it in the form n plus 1.
You need to write it as a proposition.
I don't think you really need that.
So we didn't. And then first step is prove P of 1 is true. In case P of 1 is true.
So that's
Yeah. Do we say 1?
It's for all.
Is it for all in here? Yeah. Okay.
Yeah.
So now B. Prove P.
So this is where you're substituting n plus 1 and all of those.
Doesn't really as hard.
That's where I have. Okay.
We're just gonna add.
There you have it. Do you see that smile on my face? Video.
What do you mean?
Substitute n for n
Oh, I
plus
was
1
doing
on both
it
sides.
You have to add this to both sides and make that into most of the way to where it looks like the form of n plus 1. Because if you just plug it straight in, you don't prove anything, you just plug it in. So you have to show the steps that make it work that way.
I thought, no, because we're adding an entire.
Yeah, yeah, yeah.
I'm getting
You're right, you're right.
It's
I thought you
square.
So then now you would,
Not that.
One in step 3B, 1 squared plus.
Well, we're gonna add n squared plus, I mean n plus 1 squared to
Yeah,
both
we're gonna add
sides.
n plus 1 squared, so 1 squared plus.
Don't need to write the whole thing.
So we can do this in today, how we want to do a, I don't know, for
Yeah.
And then.
Might be easier to draw from over here at this point.
You probably want to,
Yeah, boil it out.
You can get back over here. It's easier.
You think about what's in there.
yeah.
So you need to simplify this.
But again, I did all of the algebra. Do you want me to just bring it in?
you just.
Yeah, done.
I feel like there was a question there.
Oh, right, yeah.
This is a propositional chapter squared.
Okay.
So you just simplified out the top, the numerator, and took out the.
Yeah.
Would you distribute the 6/3 like this?
So what you do is you have
this side.
Plus six
multiply without everything there.
Five, six, yeah.
Would you distribute the 6 for or would you leave it out?
Distribute it.
Not me. I only go to squares. Like, I don't do cubes.
Well, let's, how about we expand that right there?
Well, I'm.
The- just the n plus
Basically,
one
no,
times n plus two
it's
plus
going
three.
into
So you
Expand
start
that.
on higher.
Just,
Form.
not even over six, just.
So that's the intuitive parts of this algebra at this point, we keep going and finish it up. The algebra gets us, you've got the inductive part, real specifically.
So we can say these factors to this.
Can't really ask technically, but. So how do we go from this to this?
It gets ugly, but let's see. You proved P of 1, you did P of n, you added that. Okay, so step 3 is the key point. So that's good. And then, yeah, just multiply the top out and you'll see it's equal to the same thing.
Multiply the top.
You should be able to.
So you've got n plus 1 times n plus 2 times 2n plus 2. If you multiply that, you'll see that that's equal to 2n cubed plus 9n squared plus 13n plus 6.
But if we didn't already know this, how did we get from here to there?
It's hard. Factoring cubics is a tricky thing. But since you know that, even if that's in your ignore area, you can still use it as long as you use it in a valid way. And you can simply say this is equal to, as long as you confirm that it is equal to that. And the teacher can just marvel at, how did they get that? But it's right. And then it's all fine.
We can say
Yeah, I'm just trying to.
Pn.
Like what will plus
Shouldn't it be n squared plus n times n plus one? On the line that you're pointing at.
Thing in red is what you're
Yeah,
after.
that's right.
Oh, okay, yeah, so you were
Initially,
initially
2 times the quantity plus 1 plus 1.
Yeah.
Yeah.
Okay.
you can multiply by 2n squared.
So this is true
Plus.
from the definition of Pn plus 1, which we
And
found.
then there's algebra.
Yeah.
So the way that would work is this, so you put 2n squared
And
under
there might be,
synthetic division, not synthetic, but
I think there's a typo somewhere.
because you have to match this one. So to get to match that one, you have to use 2n plus, and that would be 2n squared right there. And what you multiply up top is 2n. So that right there.
Just include it.
Yes.
Because I mean, I can see how it relates. If
And then
n is equal to n plus 1, this is n plus 1, n plus 2. And then n plus 1 is like 2n plus 1 plus 1 is 2 plus 2.
We can therefore be of n implies that you're
But you're,
I don't know what that is.
I see what's Are you happy with that way?
Therefore,
It's more like a thing on one side.
You can tell it is by the way it
Oh,
is.
is that the step?
Yeah, you can
This comes from substituting
So there-
whether or not we can work both sides.
Yeah, once you.
They're equal, but.
Yeah, once you.
I've had teachers tell me both. Want to show that.
So I think that means something else.
I've had.
A lot of these are really similar to just how they're
Well, we were only allowed to work at
You
one
just
time.
need to like figure out what's the negative and the sequence.
Numericals, yeah, this one's like.
Yeah, that one's, that's actually, I forget what, that's like a special problem. I forget what it's called, but it's like a super advanced engineering problem.
Yeah, I guarantee it's good.
I will do this.
so one
You can do the other one.
Okay.
comment though, so P of n is the hypothesis, assuming that's true. Over here, I'm not sure I would write P of n here. Right? The reason why this is true.
And then you should be able to factor out and then
Right? But this is definitely suspect, because now you've stated that P of n plus 1 is this, and that's not what P of n plus 1 is. Right? Your reason for writing this has nothing to do with P of n plus 1 as far as your proof. Your reason for writing this is that this is true, and you're just adding n plus 1 squared to both sides of that. So this follows from step 2, but I wouldn't have P of n plus 1 there. Because if you could write that, you'd be done. Right? That's what you want to show.
no, one that's
So there you
Okay.
can
Okay.
get all the numbers right.
I'll be shorter this time.
Right, then you can go to your ignore section and say, well, this should be equal to that, so you can multiply this out.
I know. They have a different relation
That makes like
It makes sense if you were to substitute n plus 1 in for n, you end up with this right here. So if n equals n plus 1, then n plus 1, and then you have.
No, I'm just looking at like that. Like if you, maybe you could multiply n
So if you
plus
have-
1
so the
and
two
multiply
matters
plus
plus
1 and see if you get something different than what I got.
Yeah, exactly.
Because for that, you'll get that.
How's this?
And
Yeah.
so like you multiply these two together and factor it out. So that's 6. And that's the same.
Okay.
Okay. So then,
Therefore,
n squared plus n plus 1 squared plus
And you should look
yeah, I got the same
And there's
idea
no
there.
typos right there in T when you.
He said ours was right though. He looked at ours. Did they think something different or they just like lied and said what?
Like your handwriting is like visibly worse because you're like, I want to just write this
I
down.
get that.
I wanted to do math like a dual major.
Right, the main step is.
This
This is true because you just did it.
Well.
Oh, it makes sense. I just ignore it.
definitely very organized.
This is your code state.
The eraser's right now.
That's what this is.
Oh yeah, the eraser is right here. That's the end of 5. Oh wait, no, we have 5 minutes. Because this
We have
ends
that.
at 55.
Got that right there.
You get there?
Got there.
All right, cool. So we will try some other mathematical and less mathematical examples of this on Wednesday. Cool. Good. All right, I'll see you Wednesday then.